What's up guys, and welcome to another video solution. This time we're going to solve the problem 95. It's the problem about a circuit, and the problem asks us to determine what's the current across passing through the inductor 1 right after the key is closed. Actually, I made a mistake. It asks you what's the derivative of that current with respect to the time right after the key is closed. So initially the key is open, but then the key is closed, and because of that, this whole circuit start to how can I say that? Start to work. So one way that we can do that is use the Kirchhoff law, and something that we can make also to clarify or to simplify the problem solution is put a plus sign and negative sign on the elements of circuits. So we have a plus sign here because the side of the resistor is the nearest side of the battery, of the plus sign of the battery, and this negative here, here's negative because this sign is the both side far away from the positive side of the battery. So this is plus, this is minus. Here is minus because this side is near the negative side of the battery. So this is plus, and this is also minus because this side is the nearest side from the negative terminal of the battery. And this is plus. And applying Kirchhoff law for both the, I forgot how we name these things, but anyway, it's A minus this thing, and I'll call the current, this is total current, I'll call total, passing through the resistor 1, and the current passing through the voltage across associated with an inductor equals this thing. He's total, and there is another resistor here, and I'll call the current passing through the second resistor E1. So this is E1, and I think I will not put total here in order to avoid confusing change with the letter, the number 1, because my T is very similar to the number 1. So this all equals 0. And remember, the only thing we are doing here is calculate the voltages, all of the voltages across all of the elements of circuit in this path. And it doesn't matter the way you do that. If you're going out from one point and at that same point, the total voltage change is 0. So there is no voltage here. And for the second, for the more external, let's say path, we get the same thing here, and the only thing we have to change is that the current is passing now through the inductor 2. So we get, and the current 2 is the current passing through inductor 2, at least according to me. These two equations that let's say governs the motion of the electron on the circuit. And one thing that it's quite obvious is that the total current is the sum of current 1 plus current 2. So, and one approach that we may use to solve the problem is actually substitute this expression in one of these first equations. So in my case, I substitute this expression in the second equation. So we get I think I will separate the terms with current 1, but I think I will do that later. This is E1 dt, and there is a last term here. This is 2. All of this equals 0. Put 0 right here. And one thing that we can do to make this whole equation 0 is actually put this first term. Let's put this first term equals 0, and I will explain why we do that. And the rest of the term is also 0. So this is the equation that we will use. And this is coming from the fact that when you have a circuit with an inductor and a resistor, there's a voltage difference between here, these 2 points. And so I think this is a horrible drawing, but anyway, this is L, this is A, R, and so V minus, what's the voltage? Differential potential associated with an inductor, LDA dt. What's the difference potential associated with this resistor? It's this thing. All of these equals 0, summing. So this is the same thing as the equation right above. And when you get the form of the current, because this is a differential equation, and it's easy to do that because you have a current, a term of current, and a term with the derivative of the current respect to the time, and a function whose derivative is proportional to the same function is actually the exponential function. So it's very easy to do. If you put E is the form, exponential form, you put in a coefficient A here, a coefficient let's say B here, which depends on the timing. The exponential term has a time dependent factor, and another coefficient here, and you substitute this current in these equations, you get what's the value of C and B. And you know that the current, initial current, when the time is 0, the current is 0 because you just turn it on the thing, let's say, how can I say that, the DC voltage. So when you apply this condition here, you determine the third coefficient, which is the A. And I think you guys know very well the solution of these equations, and I'll put it down here. So this is the current E1 equals the total voltage applied, DC voltage. In this case, we have minus this thing. And this is the current actually passing through, important to say, passing through the inductor 1, because the current passing through the inductor 2 is obviously different, at least for any time. So the problem actually asks us to determine what's the derivative of the current right after the key is closed. So the derivative of the current with respect to the time when the time equals 0. And when you derive this expression with respect to the time, you get minus sign with minus sign, plus sign, divided by here inductance 1, and an exponential term in here, and this time should be 0. So this exponential term is actually 1. And this R1 cancels out with this right down here. And so we get the derivative of the current passing through the first inductor is initially this, this is inductance. And if I'm not wrong, the voltage is 6 and this is 0.3 Henry. And this equals, I think this equals 20. Yeah, it equals 20. And the units of variation of the current ampere per second. So this is the solution to the first letter, which is the letter A. Now we're going to solve letter B, which is particular for us. It's better because it's more easy. So guys, solve letter B. This is the scenario. And why this is the scenario? Is this a good scenario? Because when the time is actually infinity, because the problem says a stationary solution, so the time tends to infinity, we know that the inductor doesn't work. So the inductor, which is actually a coil, which is just wires formed by wires, when the time is so long, these are just wires, they doesn't work. There's no magnetic field. Actually there is no voltage across these wires. So it's like you don't have inductors. If you don't have inductors, the current will try to choose the path with the lower resistance. So the current will go in this, follow this path. So and the way you may see that is calculated the equivalent resistance in here. Let's say there is a resistor here, R lowercase. So you have an equivalent resistance of this magnitude. Let's write that this is R lowercase plus R uppercase 2. And when the R lowercase tends to 0, this term becomes irrelevant and the denominator is R uppercase 2, and this cancels out with the term right above, and yeah, it is actually approximately the R lowercase, but the R lowercase is actually 0, or actually it's approximately 0 for a wire. So the equivalent resistance is actually 0. So you get a circuit like this one right over here. Oh, this drawing is horrible. Actually, that is just a DC voltage and a resistor. And what's the current passing through this thing? I think you guys know, it's this expression. So the A is 6 volts divided by I don't remember exactly what's the magnitude of the first resistor. I think it's 8 ohms. So this gives us, I know the answer, 75 ampere. So this is the solution to the second letter, the letter B. So guys, this is it. This is the solution to problem 95. Anyway, you guys have I hope you guys have a beautiful day. And I think I'll see you guys in the next problem. So bye bye.